Hello, I am going to continue my discussion regarding some exercises and problems that I have recently given in the Google Classroom. So we have discussed up to exercise 4. Now the fifth exercise is like this. I have two distribution functions f and g. I am creating a new function by integrating one with the another. So if you see, this is a Riemann-Stieltjes integral. Now you could do integrate g with respect to f or f with respect to g. They will be one and the same. Why? I will come to that in a minute. But the point is that the result of this integral will be a function, new function in y. My claim is that h is a distribution function, and if either f or g is continuous, so is h. Now this operation is known as convolution. So first of all, you have to verify. So let us just take this formula and verify that this is a distribution function. So you see that this is non-negative valued function. Why? Because the g is non-negative valued and f is monotonically non-decreasing. So I have mentioned that these integrals that I have mentioned are in Riemann-Stieltjes sense and improper Riemann-Stieltjes sense. So I hope you remember your Riemann-Stieltjes integral. What would be integral a to b in this function? This is roughly equivalent to if you partition the interval AB into a large number of small interval where the norm of the partition is very small. Norm means maximum length of the subinterval. So only number of partitions downward hole no hobo. Actually the norm of the subintervals should be going to 0. Then this is actually the limit of the sequence of partials, sequence of sums. Or sums ki hobo? Summation of yat likhi asu. So actually this will be sum or like I equal to 1 to n, where n is the number of subintervals of a to b hole number of subintervals of AB, where the norm of the partition is going to 0, such that g of y minus zi okay, sorry, wait, zi into dfz means d actually stands for a very small difference, z minus zi minus 1. So imagine an interval AB partitioned into a equal to z1, z2, z3, z4 up to zn minus 1, zn is equal to b. So the endpoints, at the endpoints you measure the differences, okay, f, okay, so this. So instead of the length, so instead of f, if I simply took zi minus zy minus 1, then that would be Riemann integral of gy minus z dz. Then I will zi minus zy. Since I am taking with respect to f, so this will be fzi minus fzi minus 1. Now if if f is monotonic and g is continuous, then you know that if the make the partitions refined, that is, if the norm of the partitions is going to 0, then it will converge to a limit, and that limit is called the integral. Now if you make a and b larger, so if you are kind of having a partition of the of ab, where ab are arbitrarily large and the same thing goes through, then again the limit is called the improper Riemann integral. So roughly it is like you are partitioning the real line into arbitrarily small, you are having a countable partition of the real line where the length of each subinterval is very small, and then you are looking at the partial sum. So and then you are taking the limit over n. So therefore that is the basically idea. So therefore basically it is a sum like this. Anyway, so this is just a digression from the main discussion. So what we need to prove is that this is non-negative valued, first of all. So see, since f is monotonically non-decreasing, so therefore these terms will be non-negative and g is non-negative. So therefore this is a non-negative valued function. Why? Because since g is a distribution function, so and f is distribution, both are non-negative and monotonically non-decreasing. So therefore in this case h is monotonically non-decreasing, and you can verify that since g is between 0 to 1, so therefore this integral will also be between 0 to 1. So if you put 0, then it is 0, and if you put 1, then it is f of minus infinity minus f of f of infinity minus f of minus infinity, which is 1. So this integral is bounded between 0 to 1. So therefore you have got monotonic. Also g is monotonic, because if you take y1 and y2, so g y1 minus z will be less than equal to g y2 minus z for every z. So therefore the monotonicity will also be preserved. So in this way you can verify, and then you can prove that this is a right continuous function. Of course, to take the limit under the integral, you will need something called the dct, which you will hold here, because because g is bounded. So therefore in this case, using dominated convergence theorem, you can also prove that h is right continuous. So in this way, these are some important properties. So we can prove that h is a distribution function, and in fact one of the distribution functions, since suppose g is continuous, then by dct again the limit will come under the integral, because g is bounded. So bounded continuous function hole, that the dct will hold, because you are taking integration with respect to a distribution function. That means here if it is dominated by 1, so and 1 is integrable here, because what is integral of 1 minus infinity to plus infinity dfz, that is 1. Therefore by dominated convergence theorem you can take the limit under the integral. And so the story is that this is again a distribution function, and this distribution function is called the convolution of these two distribution functions, and if one of them is continuous, then the resulting distribution function is also continuous. So the last argument probably I should write that if g is a continuous continuous distribution function by DCT, dominated convergence theorem, I hope you are all aware of the dominated convergence theorem, right? The point is that it is a theorem related to when you can take the limit under the integral. You cannot always take limit under the integration. So dominated convergence theorem provides a sufficient condition under which you can take the limit under the integral. So let us say y right arrow y naught, say y1, y0, this will be equal to integral paste. So instead of y, you will have this limit y naught. So that is coming from the dominated convergence theorem. So that is coming from the dominated convergence theorem. So therefore what we have proven is that this new function, so this is actually limit of h. So you see this thing is actually copy h of y. Eto hoyto tomaloker karone okoman this is a bit advanced, but anyway this is an important property. So this is h y naught. बाकी जेटा कथा मैं कहलु तेनेकुआ you can verify that h minus infinity is 0. So by the same logic you can take the limit under the integral. So h minus infinity, g minus infinity is 0, so it will be 0. Similarly h plus infinity is 1, so it will be limit y tends to infinity, this thing, so it will the limit will be pushed under this, and therefore it will be 1. So in this way we can prove all these properties. So this is called convolution. And now here is a very important fact. Just let x and y be two independent random variables with f and g as distribution function. So you have not studied what is independence, but we will come. So let us for a moment put it as italics. This is something we have not understood till now. Just let it be there. Then h defined is the distribution function of x plus y. So this is also we will show. So this what makes this exercise very important, that h which you get in this peculiar way, which is called the convolution, that is actually the distribution function of sum of two independent random variables. It is of great value to know even this, even although you have not yet studied what is independence of random variables. But the fact is that this new function is a distribution function, and its interpretation is that you have it is the distribution function of the sum. So these are some important exercises. Then of course let me add another problem. So you think over this EXERs. Here you see exercise 5, 6. So if I have got PAN is equal to one by n square. Okay. Can you say something about probability an infinitely often? So hints I am leaving as hints is Borel-Cantelli lemma. So this is something I am giving you as a exercise. I am not telling you, but the hint should be enough. Okay. Please have a look at this exercise. Thank you.